Hey guys, welcome to part 3 of the Fluid Mechanics mini course. This video is going to focus on pressure as it relates to the depth within a fluid. If you're like me, as a kid, when you would swim down into the deep end of the pool, the deeper you would get, the more pressure you would feel on your ears and your sinuses. If you've been lucky enough to scuba dive, you know that the deeper you go, the higher your pressure gauge reads, and the harder you feel the water pushing on your face and your body. It goes without saying that pressure is definitely affected by the depth within a fluid. In this video, we will explore the mathematical relationship between pressure and depth, and then take a look at a few other factors that could affect the pressure within a hydrostatic fluid. Let's get started. So far, from parts 1 and 2, we have already established that pressure is defined as the amount of force per unit of area. We've also shown that the pressure within an enclosed fluid is transmitted undiminished throughout that fluid. In part 2 of this fluid mechanics series, we focused on how pressure is transmitted evenly throughout an enclosed fluid. We looked at the mathematical relationship between force and pressure and established how when there's an equal pressure, a fluid is static. Let's take a look at what happens when there's an unequal pressure between 2 points in a fluid. If we focus on a little block of water that makes up a bigger container of water, we can see that an unbalanced force acting on this little piece of water would therefore translate into an unbalanced pressure. So when there's a pressure difference, there's a net force or a net pressure pushing in one direction, and the water molecules will thus move. The fluid molecules in general will move until the pressures have evened out. This is very similar to a potential difference. When charge is separated and a potential difference is created, that potential difference constructs an electric field, and thus charges can be pushed within that field. When there's no potential difference between 2 points, charges don't move. It's very similar with fluids and pressure. When there's a pressure difference between 2 points, there is a net pressure pushing in the direction from high to low pressure. The result is that fluid particles will move when there's a pressure difference. We'll get into this in a lot more detail in an extension video that will come at the end of this 4-part series. Let's imagine a point in a beaker of water deep down near the bottom. If we analyze that point in the water, we could say that there's a whole column of water sitting on top of that point. Now that water has mass, and so it's as if there's a huge stack of water plates sitting on top of that point, exerting a force and therefore a pressure on that specific point. It goes without saying that the deeper the point is located, the more plates of water there are above that point, and therefore the heavier the column of water is above that point. If we wanted to mathematically describe the weight of that column of water above the plate, what we could do is write that the force that is exerted on that point is equal to the pressure at that point times the area. This is just manipulating the definition of pressure, which is the amount of force per unit of area. Now the force is specifically the weight of that water above. The weight is the mass times the acceleration due to gravity. Now if you recall from the previous 2 videos, we've said a few times that instead of writing a fluid mass, we'd rather substitute in the fluid density times volume. So if we substitute in density times volume for mass, multiply by G, and set that equal to P times A, we're on our way to figuring out a relationship between the depth within a fluid and the pressure at that point. The V in this equation that we've written so far refers to the volume of that column of water above the point in question. We can substitute the expression A times H for V, leaving us with rho times A times H times G is equal to P times A. Now we can very clearly see that the A variable, the area variable on each side of the equation will cancel out, and I'll be left with pressure is equal to rho, the density of the fluid, times H, the height of that column of water, times G, the gravitational field. Now this H, the height of the column of water, is analogous to the depth within the fluid. The equation supports the idea that depth and pressure are directly proportional. If I were to graph the pressure versus the depth in a fluid, I would get a direct relationship. This would only occur for a uniformly dense fluid. Looking at the equation we just derived and the shape of this graph, what do you think the physical meaning of the slope is? Pause the video for a few seconds and try to figure that out for yourself. Hopefully you can tell that this graph is in the general form y equals m times x. Here, y is represented with pressure, x is represented with h, and if we look at the equation that we just derived, that leaves rho and g, the product of rho and g, as the only constant variables, and therefore rho times g is the meaning of the slope. If we took a beaker of water, knowing that the density of water is 1,000 kilograms per meter cubed, and the gravitational field strength is approximately 10 meters per second squared, or newtons per kilogram, the slope of this line should be 10,000. If we analyze the units of the slope, which is the density times the gravitational field, that would be kilograms per meter cubed times newtons per kilogram. The kilograms would cancel, and I'd be left with newtons per meter cubed. Now that's not exactly a pressure unit, but once I multiply the slope times h, which is the independent variable, a meter, we see that a meter will cancel, and I'll be left with newtons per meter squared, which is a Pascal. So each meter that I go below the surface of the water, the pressure increases by 10,000 pascals, or 10,000 newtons per meter squared. So to summarize, we would say that to calculate the pressure at this particular point below the surface of, let's say, a beaker of water, I would take the density of the fluid times the depth that I am within the fluid times the gravitational field. Now you may have been wondering the whole time, well, what if I extended that column not just of water, but of all the air that's sitting on top of that same place? Shouldn't that factor in? It most certainly does. If I actually graph pressure versus depth, as we discussed a few minutes ago, the line that results if I collect data will actually have a y-intercept value. So this equation would be written more specifically as y equals mx plus b. Now y is pressure, as we've already discussed. The slope is rho times g. The independent variable, or x, is h. And we can see that the y-intercept is just an initial value of y, or an initial pressure. Basically what that's saying is that's the pressure at the surface of the fluid, and whatever other fluid or gas it comes in contact with. So that's the pressure at the surface of the water-air interface. We usually refer to this P0 as atmospheric pressure. That is a very specific value of pascals, oftentimes written in atmospheres to reduce the number of digits you would have to write. So let's say I had a column of 3 different fluids, and they all have different densities, and so they separate out. I have one fluid on the bottom, I have another fluid in the middle, and a third fluid on top. If I want to figure out the pressure, let's say right down here within the fluid that's at the bottom of the column, I would have to take the pressure up to that point to the interface between the bottom and the middle fluid, plus all of the weight of the fluid that's in the middle, plus all of the weight of the fluid that's in the top section, plus the atmosphere. So what I would literally do is write the pressure at this interface right here, P0, plus the pressure at this interface right here, let's call that P1, plus the pressure at this interface right here, we'll call that P2, plus this amount right here, which we've shown we can write the expression rho times G times H. And I would just add all of those up to get the absolute pressure at that point way down here in the bottom fluid. So all in all, I would write P is equal to rho times G times H plus P0 plus P sub 1 plus P sub 2. And I would keep adding pressures for however many different kinds of fluids there are above the point in question. You can hopefully see that this would allow me to account for different densities in each of those sections of fluid. Now, it's not a continuous spectrum. That would probably be better suited for a calculus problem, but for what our purposes are right here, we can say that each of these different fluids has a different density. And so in essence, I could really substitute in the expression rho times G times H for each of those sections of fluids, using the total depth of just that section for the height in the term. We refer to this equation as the pressure in a hydrostatic fluid at some particular depth. In the next video, part 4, we will focus on how the difference in pressures between two places at the surface and someplace below can actually create buoyancy in the water for objects that are placed within it.